This video is about the system I use to take a typed sentence and use it to animate my robotic mouth. So in speech, you can describe a phoneme as a unit of sound that makes up a word. A viseme, on the other hand, is the way the mouth looks when certain phonemes are being made. So you could describe it as like a mouth position when a certain noise is coming out of your mouth. So the control methods that I've used so far focus on finding a phonetic translation of a sentence and then translating this into a sequence of phonemes, which are then sent to the animatronic mouth and expressed as a sequence of mouth poses or visemes. Before any of that can be done though, visemes need to be configured for each mouth shape we want to use. So this is the reason that I built the servo tester a few videos ago, because I wanted to be able to pose lots of different servos simultaneously to get mouth positions for different visemes. So I used my servo tester to find the position of each of the 9 servos in the mouth mechanism in the different visemes I wanted to use and wrote these into arrays in my Arduino program. So even though there are a ton of different phonemes and visemes, for my purposes I simplified it to just 8 poses, 8 visemes, because a lot of them actually look really similar. It would be possible and quite easy for you to modify my code to add a load more different poses into the code, but the poses that I've got are for the sounds A, O, B, G, TH, like th, L and F. So once you have all of these visemes programmed into arrays in the Arduino program, that's all that's required for the most simple form of speech synthesis that you can do, which you can do with one of the programs in my download package, the Arduino program called Mouth Basic Phoneme. So using this program, you can simply tell the mouth to pose for a specific phoneme using the phoneme pose function. You can queue a few of these poses up according to a sentence you have in mind, and then add a delay between each pose. Now, that would be really time consuming, but theoretically it could be quite accurate. You could get all the timings perfect to audio sample that you have, and you could make it look really good. But what I was interested in was finding a way to sequence visemes from a user input. So the first method that I used to speed up the process of sequencing the visemes was to use the Arduino serial monitor as an input for a user's sentence. I then wrote some simple code that separates the sentence into each letter using a function called phoneme match. And the way that it was programmed is essentially just a great big block of if statements. The input comes through the serial connection, each letter is looked at by the code, and if it's an A, it poses for the A phoneme, if it's a B, it poses for the B phoneme, and so on. There is a little bit of difficulty with the TH phoneme because obviously that's 2 letters, so if the program detects a T, it waits for the next letter before deciding whether to use the phoneme for T or TH. Again, it's really simple to achieve this with if statements, so it's not a very complicated program at all. None of this is really. Now in terms of realistic lip syncing, this method is not very good because, as we know, words are never really spelled to be spoken letter by letter, at least not in English, so the results produced by this method would not be very realistic. It's a good way to see if everything's working with regards to the mouth poses, and if you spell words phonetically, then it can work fairly well. So the next stage that I moved on to was to use Python and use some libraries in Python to find a much more accurate phonetic translation of the words that I typed into the program. So the way that it does this is by using the NLTK library in Python, which stands for Natural Language Toolkit. The user enters a sentence which is separated into each individual word and the spaces are discarded. Each individual word is processed by the NLTK library, which looks up the words in the CMU pronouncing dictionary. This output gives the phonemes in alphabet format. Now, alphabet is a set of phonetic transcription codes for American English, which is much more condensed than the IPA, which you might have seen in dictionaries and wherever else. So alphabet is designed for American English. I'm not sure if there's an English equivalent, but if there was, I'm told that it probably wouldn't be much use to me. So the format for the alphabet codes are a string of 1 to 3 characters. So 1 or 2 of the characters are for the sound that's made, and then sometimes there's a number on the end to indicate the stress on that particular phoneme. So the stress can either be a 1, a 2 or a 3. 1 would be indicating primary stress, so that would mean you sort of linger on that sound for quite a while. 2 would be secondary stress, so it's like less of a stress in the word, but you still sort of stress that particular sound, and then 3 would be tertiary stress, but I don't think that's actually used. You can also have a 0, which would indicate no stress, and this is kind of where you like skip over a sound. So these strings are then printed to the serial port, which takes it from my computer through the USB port into the Arduino, which then decodes the character strings. The Python script also puts a full stop or period in between each phoneme, and then at the end of it there's a dollar symbol to indicate the end of the phrase. The Arduino then looks at each incoming character and matches it to one of the phonemes that we defined earlier. It poses the mouth as it's reading the incoming data, and then depending on the stress, it decides how long the pause should be between each individual phoneme. So if there was a 0, that would be no stress, and it would have a really short space in between that phoneme and the next. If there was a number 1, that would be primary stress, so it would be a longer delay on that particular sound. If there was no stress indicator number, then it would just be a sort of average speed. It's trickier than with the previous method because the length of the phoneme code can be anywhere between 1 and 3 characters, so the code must check 1 character ahead before posing the phoneme to see if there's either a stress indicator or period to indicate the end of that phoneme. So this is executed with essentially a disgustingly massive block of if and else if statements, but if you're willing to dig into it, you'll see that it'd be quite easy to add more visims and potentially have a fuzz for every possible phoneme in the alphabet, which could potentially give you really realistic lip syncing results. Now I must confess that this was actually my first time using Python, so I was just running the program in Visual Studio Code and starting by plugging in the Arduino through USB, then the servo driver power, and then running the Python program. I'm sure there's a ton of stuff that can be improved with my program. I would really love for someone to take it and improve on it, but I think of it as just sort of like a starting point really to something more. There's just so much more stuff that could be done with it, but I'm going to talk about future work in a minute. So do note as well that if you want to use this, you'll need to install the PySerial and NLTK libraries. So future work, as I mentioned, I feel like this is really just scratching the surface of what's possible, and I just kind of wanted to put this out there to start the conversation on different ways of controlling the animatronic mouth. So here's some ideas of improvements I'd like to see to this program, or potentially entirely different ways of posing the mouth. So firstly, as mentioned, it should be really easy to add phonemes to the program. There's something like 36 phonemes in the alphabet. You could at least have a mouth position for each individual phoneme in the alphabet, and that could give some really nice realistic results. Since the mechanism that I've been testing with is actually quite simplistic, it might be a good idea to use a more intricate animatronic mouth design with more degrees of freedom, which is another thing that I'm interested in developing at some point. One thing that I really wanted to do was to be able to pose the mouth in real time according to a microphone input, but I just couldn't figure it out. So to start off, I used the speech recognizer library in Python, and you can quite easily speak a sentence through a microphone. It'll be converted into text, and there's even some ways to make it offline, but normally it just looks it up with Google and gets a really accurate translation. So with that method, it obviously doesn't take into account any information further than the text itself. So any information about the voice actor's performance, stress on different parts of the words, accent or whatever else, it's all lost unfortunately, and it's also not real time. Using the Pocket Sphinx library in Python, it is possible to have a live phonetic translation of a microphone input and convert it into alphabet phonemes, but I really couldn't get this working well enough to be able to demonstrate it. It just wasn't reliable enough and not at all instant. The error rate of the phonemes were actually really high. I know that it's possible because I've seen video games like VR Chat as like live lip syncing. I think even older games, I think Gmod had it even. But I think maybe they weren't anywhere like as accurate as I sort of have in mind, so that's something that definitely needs some work by probably someone who knows a bit more about programming than me. So the ultimate solution would be to use motion capture, and there are open source motion capture solutions which are actually built in Python and use Blender and stuff like that, so presumably it would be quite easy to incorporate into a similar system to the one I have right now. Motion capture, however, is not great for tongue movements, and I haven't really been able to find any motion capture solutions that can incorporate tongue movements. So what I would propose is that the best solution would be to use motion capture on the face for mouth and jaw movements, which can then be directly mapped onto the motors of the animatronic mouth. But then simultaneously, if you had a program that listens to an audio input, corroborates with the motion capture data, and makes a best guess for the phoneme being spoken at that moment in time, I reckon that'd give an absolutely fantastic lip syncing to an animatronic mouth. So I really hope that you've enjoyed this video. The next video that I'm going to make is actually going to be about my bionic hand. So a huge thank you to all of my patrons, everybody who supports me on Patreon, and I'll see you in the next video.